So hello guys, here we have problem of the day 355 from the Physics Olympiad Discord server, the link to which is in the description. You can check it out once. So yeah, let's start. Two particles of mass m are connected by a light string of length L. One of the particles rests on a horizontal table in which there is a hole. The string passes through the hole so that the second particle hangs below the hole vertically. Assume the hole to be origin and describe the position of the particle on the table by polar coordinates r and theta. Okay, so the first part is write the formula for angular momentum of the particle in terms of r and d theta by dt. So for the first part, here is the diagram. What we can write is angular momentum equals to mvr and m times v equals to r times d theta by dt multiplied by r. So it is L equals to mr square d theta by dt. For the second part, they have asked us why is this quantity constant. So basically here no torque is acting on the system, so it is constant. So yeah, no torque. Okay, so for the part 3, find the formula for the sum of energies of both the masses in terms of r dr by dt and d theta by dt, and show that dr by dt whole squared equals to a minus b over r squared minus gr, where a and b are constants and g is the acceleration due to gravity. So here the kinetic energy for the particle on the table is, for the part 3, the kinetic energy for the particle on the table is half times m times dr by dt whole squared plus r squared times d theta by dt whole squared. And similarly the kinetic energy for the particle which is hanging ke2 will be half times m times dr by dt whole squared. Now the gravitational potential energy for the particle on the table will be a constant. It won't change in this motion. And for the particle 2, it can be written as u2 equals to some constant minus mgl minus r. Okay, and this can be written as some constant c prime plus mgr. Here we are not interested with the constants, so ignoring them, and so the total energy what we get is equals to E equals to m times dr by dt whole squared plus gr plus r square by 2 times d theta by dt whole squared. So from here dr by dt whole squared equals to E by m minus gr minus r square by 2 times d theta by dt whole squared. And the third term here, this can also be written in the terms of L, or the angular momentum, and this can be simplified to E by m minus gr minus L square by 2m square r squared. So from here, as the energy is constant and L is constant, this equation is finally what we had wanted, and the constants a and b we required, we get those to be a equals to E by m and b equals to L square by 2m square. So this was for part 3. Now for part 4, we are given that the particle is initially at a distance of L by 2 from the origin and is travelling at a speed u in the direction at perpendicular to the string. We have to obtain a formula for dr by dt whole squared when r equals to L. So from here, solving for the fourth part, what we get is r naught equals to L by 2, dr by dt equals to 0, and r d theta by dt equals to u. So from here what we get is d theta by dt equals to 2u by L. So from here the value of angular momentum, which will be constant, comes out to be ml u by 2. So from here the constants we found in part 3 come out to be constant a equals to be u square by 2 plus gl by 2, and b equals to L square u square over 8. You just have to put in the values, initial condition values in the above equations, and you will get these. So from here, for this, the dr by dt whole squared, the equation we found in part 3, comes out to be a minus b by l square minus gl, and I have substituted r equals to l, and substituting the value of a and b, what we get is dr by dt whole squared for part 4 to be 3u square by 8 minus gl over 2. So this is the answer for part 4. Now on for part 5. Now on the basis of previous parts or otherwise, find the conditions such that the particle usually below the table doesn't pass through the hole. Assume this string to be taut at all times. So from here, for the lower particle to not pass through this hole, the value of dr by dt should not be 0 at any value of r from 0 to L. So if this condition is true, then the ball below the table won't pass through the hole. And for the limiting case, the dr by dt should be 0 when r equals to L. So from here, the condition that the ball won't pass through the hole is dr by dt whole squared, or dr by dt simply, equals to 0 when r equals to L. And this is just what we calculated in the end in part 4. So basically 3u square by 8 equals to gl over 2 in the limiting case. So from here u equals to root of 4gl by 3. Now this is the case when it is just about to pass through the hole, and so the velocity should be less than this so that it doesn't pass through the hole. So u is less than root of 4gl by 3. This is the condition that the ball doesn't pass through the hole. Thank you.